So we want to sketch this cubic graph, and with calculus, if we find our stationary points, that will tell us if they're maximums or mins or stationary points of inflection. And then our second derivative will tell us if we have an inflection point. So we find our first derivative, set it equal to 0 to find our stationary points. It factors nicely. We get 4 and negative 2. We do our sign diagram, and I'm going to add on here in orange that the signs come from f prime, and increasing and decreasing tells us about our original graph. So our original graph is increasing to -2, then decreasing to -4, and then increasing afterwards. So that tells us we have a local max and a local min. We can find these y coordinates of the actual points on the graph by plugging into the original equation. So again, we have to know which equation we're plugging into. The sign diagram, you're plugging into your derivative. For the actual points, you're plugging into your original equation. Then our second derivative, set it equal to 0, we get 1. Concave up and concave down. Again, the sign diagram comes from f double prime. The concavity tells you something about f. So we label those 3 points. It is concave down, left of 1, concave up, right of 1, and you can draw your graph. The polynomial functions are the most fun to do with calculus because the derivative is super easy. But we'll get to more complicated ones as well. So this would be a graph that we did not graph during grade 12 because we didn't have fractional exponents other than square root graphs. So if you wanted to graph this, again, we're going to find our derivative. We are going to set it equal to 0. Move the 1 over, multiply both sides by the cube root of x, and solve for x by cubing both sides. But notice in this one, we also have a non-permissible value. So when we're doing our number line, our number line has 2 points. The 8 is a stationary point. The 0 is a critical point. Our critical point still might show up as it does in this one as a minimum, but it won't necessarily be. Sometimes it could be an asymptote. Sometimes it could be something else. In this point, it's going to be a corner or a cusp. Find your second derivative. And our second derivative still has a non-permissible value. See if I have it underneath here. Yes, there it is. So we still have something where we can check. But in this case, it's concave down. When you plug things into the second derivative, it's concave down both times. Again, the sign diagram tells you increasing, decreasing about f. The sign diagram from the second derivative tells you concavity of f. And if we actually want to find that point, 8, 4, and technically I would also find, plug in 0, and I'm going to get 0 minus 0. 0, 0 as my local min. And it actually has a sharp point, a corner or a cusp at 0, 0. I briefly already showed you the answer for this one last class. I don't know if you remember. We want to show that something doesn't have an inflection point. It's not enough just to show the second derivative equals 0. Inflection points happen when the second derivative equals 0, and you still have to show on the number or on the sign diagram it changes sign from positive to negative or negative to positive. But on this one, if I find my first derivative, and then I find my second derivative, because of the nature of this question, it's not asking me to graph, I don't need to make my number line for my first derivative. I just need to look at my number line for my second derivative. So even though it equals 0, it doesn't change concavity. That's the main way that I would show it. There's also a way to show it with the first derivative. Since at 0 it changes sign and is a minimum is never going to be an inflection point. But I would use the first explanation. But at every inflection point, the first derivative will never change sign. So it is a secondary way to show an inflection point. If the second derivative equals 0 and the first derivative does not change sign, then it will be an inflection point. Here, I'm going to hand out quiz number 2 for you. Here is our second derivative test. The whole reason the other day I was changing words. The second derivative test does not find concavity. The second derivative test is another way to find maxes and mins. And it's less intuitive than the first derivative test. So if you're given an option, hey, find a maximum or minimum, you will 100% of the time want to use the first derivative test. That's normal because it's easy. In order to use the second derivative test, you almost have to ignore the first derivative test, which is hard to do. But it is another way to find maximums and minimums. So a reminder, what was the first derivative test? The first derivative test, first you found out where f prime of x was equal to 0. Then you made your number line for f prime of x. And if it changed from plus to minus, you knew you had a maximum. That's the first derivative test. The second derivative test says the following. You, again, find out where it's equal to 0, but for whatever reason, you decide to skip this. There we go. You're like, I didn't even see that that happened. You just skip that, which is very hard to do because when you graph things, you will naturally do that next after finding the first derivative. Okay? But the second derivative test says you still find this, you skip that, and then you go to f double prime of x. And if the point C made it equal to 0, and if at point C it was concave up, the only possibility then is a maximum. You see it? And if it was concave down, then the only possibility would be a minimum. And so the second derivative test says if you know the first derivative is 0 and you know the concavity at that point, you can determine if it's a max or a min as a result. Okay? So if it's concave up, oh, I went greater than 0 and I drew it the wrong way. I'm sorry, I'll just do a little erase. Like, what are they? There we go. This would be, concave up would be a minimum. So if you have concave up and you knew it was flat at that point, the second derivative test says that is enough to say it's a minimum. And if it is equal to 0 and concave down, that is enough to say it's a maximum. So sometimes the exam does specific kinds of things to see if you know the second derivative test. But if you naturally are graphing from the beginning, you will never use the second derivative test because the natural progression is find your first derivative, draw the sign diagram, and you will have increasing, decreasing, and already know where your maxes and mins are, and then you do your second derivative. You have to purposefully skip this to do the second derivative test. But it might be in a question that they tell you in a multiple choice, hey, the first derivative is equal to 0, and the second derivative at that point is 7. What can you tell me? Is it a maximum? Is it a minimum? Is it a stationary point of inflection? Is it just a regular point? That would be how a multiple choice question could test to see if you know the second derivative test instead of doing it all. So we're going to use the second derivative test in this question specifically to show their maxes and mins. It's an x cubed graph. So you would find your first derivative and you would find your second derivative and kind of skip your number line for the first derivative. It's really hard for me to skip the number line for the first derivative. But we're going to do it. So the question is 2 a maximum, a minimum, or neither? Is negative 2 a maximum, a minimum, or neither? Without doing my number line for the first derivative. So my first point is at 2 comma negative 11. And if I plug 2 into my second derivative, I get 12, which is concave up. And if you draw concave up, that's enough to say it's a minimum. And if I plug negative 2 into my original equation, I get 21. And if I plug negative 2 into my second derivative, I get concave down, which is enough to say that it's a maximum. I do have a point of inflection on this graph because it changes from concave down to concave up. At 0,5. I so badly I still feel like I've left out this number line. I so badly want to have negative 2 and 2 and show that this is positive increasing, negative decreasing, positive increasing. Feels wrong to have skipped that when graphing. But then I would have found out my maxims and mins with the first derivative test. And this question wanted me to show it with the second derivative test. I'd like you to try the next one on your own. You can use the first derivative test. I will put up the answer in a bit. There you go. All right, I'm going to put up the answers. You can check if you're done. If you don't want to check yet, that is fine. I'm going to add the number line for f prime of x if you did it, so you can check if it had 0 and 6. So had you done your first number line with, you would have found out that 0 was a stationary point of inflection.